second method box of parametric bootstrapping. Now we are going to compare two samples, not only one samples. So I'm going to do a confidence interval for the comparison of two features, for the difference of two features. It could be the difference of two means, but it could also be the difference of other features. It's the same, right? It's the same procedure, just in a double version. I'm struggling with this one here. I'm gonna smash it the last day. Method. Two sample confidence interval for any feature comparison by parametric bootstrap. Simulate from each of the two distributions. And I skipped the footnote now, but it's the same thing. The footnote is there, even though I didn't put it. Choose the right distribution from each of them, or maybe the variance also if needed. Then simulate from the two distributions, so 100,000 from each. Compute all the differences, the 1,000 or 100,000 feature differences, not only for one, but for two of them, and compare them. And look at the results. Look at the distribution. Read off the quantiles. Here's your confidence limit for the difference of two features. Same thing again, but now applied double for the difference. I believe I brought an example. What about the difference of exponential means? Meaning, let's assume I have two exponential populations or a sample from two different waiting times systems. So I have a day 1 data. It could be two different time points. I have day 2 data. And I want to do a comparison of these two exponential means. What do? I set a high k. I simulate, I compute, I look at the quantiles, right? So when I simulate, I have to do it twice now. I have to do one time I'm simulating exponentials with a mean of x, and I'm simulating exponential with a mean of y. So I simulate each of the two exponentials. Then I compute 100,000 means of x's, 100,000 means of y's, subtract them from each other, and I look at the quantiles of those differences, and I get a confidence interval. Would the hypothesis test, even though we really don't do hypothesis tests today, but if we were to do it, would we accept or reject the hypothesis of these two means being equal in this case? So now I'm doing a hypothesis test of two exponential means. I didn't teach you that. What would you think? How many believe that we could accept the null hypothesis of these two being equal? How many believe we could accept the null hypothesis that these two are the same? How many really believe they're the same based on this number? Well, it gets fewer and fewer, so don't ask 3 times. 2 was the best number of times to ask. Yes, of course, they're the same because the 0 is in the interval, right? 0 is in the interval, so 0 is a potential acceptable value for the difference. So I would accept a hypothesis of those two being the same. This is this analogy of hypothesis testing and confidence intervals that we can also use here. Right? We couldn't reject the idea of those 2 days having the same rate of calls in this call center. So, what I did so far to sum up on the parametric bootstrapping, we assume some distribution. We saw examples of the exponential. Could be the normal with some odd feature. It could be log normal. It could be uniform. It could be anything. I've given you 2 method boxes. I've given you a 1 sample method box and a 2 sample method box. These are boxes for any kind of features, but it could just be the means as we've known previously. But that's how it is. Question 7 of 9. Oh, there it is. Recap question. Good. That's okay. We had a situation of high power. The power was 90%. That's the relevant size of power, right? Power should be high, 80-90%. And those outputs, it told us 22 observations in each group. That was a recap of last time, power. Baguette is back in business. So that takes us